Good morning to everyone. Today we are going to learn about semiconductors. Today we are going to learn about semiconductors. That means what is semiconductor, what are the properties, how we can generate semiconductors, different types of semiconductors. So let's see what is our objectives of today's class. That means class learning objectives or CLO. We have several CLOs today, at least 7. CLO 1, basic idea about semiconductor. I think you are more or less familiar with the word semiconductor because in last few classes I have mentioned about the semiconductor because we are studying that about silicon, germanium, no, not germanium, boron and silicon. So in that time I have mentioned several times about semiconductor, and also you have learned during your SSC courses, so you are familiar with the word, and also few topics you are very familiar. However, we will have a little bit more elaborative description. So list of semiconductor materials, that means what are the different types of semiconductor material that we can have. Then we will show the band energy diagram of a semiconductor. So simple band energy diagram, we are not going to very complicated one, because if we consider that the intrinsic property or extrinsic property, if we add some external material, in that case the conductivity of semiconductor will enhance or increase a lot. But in that case the individual property of a crystal, we will consider the individual property of a crystal or a unimolecule. However, if we consider for a big crystal, in that case the energy diagram will be very complicated, so we are not going to there. So now another thing, variable conductivity of a semiconductor, that is actually the property of a semiconductor or semiconductor material. So if we add some doping agent or doping material, in that case we can vary the uh, capacity or the current probability of flowing current by changing or by varying the amount of the dopant. In that case the conductivity of the semiconductor can vary quite a lot. Then intrinsic and extrinsic semiconductor, that means what are intrinsic and extrinsic semiconductor, and then finally we will learn about the p type and n type semiconductor, because when we add some external material, depending on what types of material we are adding, we will get p type or n type semiconductor, that means electron donor or electron acceptor. So that is our objective, that means we will try to learn these 7 topics today. So let's start from the beginning, that means the basic idea about semiconductor. So you are familiar with the metal and non-metal and also semiconductor, but what is semiconductor? Any material in between the in property, if you consider about the property or conductivity, if a material has a conductivity in between a metal and a non-metal, in that case we can consider that metal or that element as a metalloid or semiconductor. So if we consider the gap between the valence band and the conduction band, actually what is the valence band and what is conduction band? Here you can see the figure. This is the valence band. That means if we consider the electronic configuration of an atom, in that case our outermost shell is considered as the valence band. But if you need to transfer some current or electricity, in that case you need to have some other imaginary conduction band. Imaginary conduction band, that means if the conduction band has some electron, it should be always if it is available, either it can be partially filled or empty, but completely full filled conduction band is not available. So here you can see this is a metal, this is also a metal. Here you can see the conduction band. That means if you consider two bands, valence band, valence band is lower energized and the conduction band is upper energized or higher energized. So sometimes the conduction band can be empty or sometimes it can be partially filled, but it cannot be completely filled, the conduction band. So when any element has some free electron that have that can have the conduction band partially filled, but sometime you may have or not free electron. Therefore if you do not have any free electron in an atom, then there is no possibility to conduct the electricity or heat. Therefore what about the metal? Some metal have partially filled or completely filled the valence band. However, if they do not have the partially filled conduction band, in that case it is very difficult to conduct electricity. So most of the metal has some free electron so that it can conduct electricity. Or when you apply some potential difference between two end of the metal, in that case the due to the potential difference the electricity can be transferred. However, if there is no partially filled or minimum, if there is no free electron, in that case no electricity or heat can be transferred. So in case of metal, some metal what can conduct electricity very fast, they have the conduction band and the valence band. The conduction valence band and the conduction band are overlapped. Here you can see this band, this is the valence band and this is the conduction band. In that case they do not have overlap or there are quite a large gap in between the valence band and the conduction band. So to transfer electricity you need to apply quite a high potential difference so that the electron from the valence band can transfer to the conduction band. But some of the metal has their valence band and conduction band almost overlap or completely overlap. Therefore it is very easy for them to conduct electricity, like as copper. So in that case just applying certain potential difference, or if you put very little potential difference between the two ends, then you can get the electron can transfer from valence band to the conduction band. So from here to here it is easy to transfer the electrons, but from here it is not easy. So many metal conduct electricity very fast like copper, but some of other metals do not conduct electricity as good as copper, because for some metal they have filled valence band but empty conduction band. So if they do not have free electron in the conduction band, or the gap, if the energy gap between the valence band and the conduction band is large, in that case it is very hard to transfer electron from the valence to conduction band. So it is not very good conductor. But for some other metals their conduction band and valence band are mostly overlapped so that they can transfer electron very easily. What about the insulator or non-conductor? In case of non-conductor or insulator, their valence band is completely filled and the conduction band is completely empty, and the difference between the valence band and the conduction band is very large. Therefore if you applied quite a lot or quite a large potential difference, still it is very difficult to transfer electrons from the valence band to conduction band. So it is very hard to flow electricity through this insulated material. However, if you apply very high temperature, in that case this band gap, energy band gap, can decrease a little bit, and the energy of the electron in the conduction valence band due to increase, or the kinetic energy of that electron, they can transfer very little bit energy, or sorry, little bit electron from the valence band to the conduction band. So at higher temperature the insulator can transfer some of the electrons, but at room temperature or normal temperature or very low temperature the insulator cannot transfer electron at all. So we can say from here, due to having the valence band completely filled and conduction band completely empty, and the difference between the energy, or the energy difference between the valence band and conduction band is quite large. This is the band gap. We will consider the energy difference between the valence band and the conduction band is band gap. So the band gap for these two bands are very large in case of insulator, so their electrons cannot be transferred from the valence band to conduction band. But in case of semiconductor, the band gap is quite small compared to insulator. So here you can see the band gap from here to here little bit shorter compared to this. However, the conduction band has some electron, that means partially filled or slightly filled. So it has some minimum electron in the conduction band, or the difference between the energy or the valence band and the conduction band is quite low. Therefore, if you apply some potential difference, the electron from the valence band can transfer to the conduction band. Or due to having the difference, if you have some ladder, do you know the ladder or stairs? If you want to go in the top floor of a building, then you need to overcome some stairs. So if there are very big stairs, that means maybe normally how we climb to a building, in that case we have some stairs what we can easily overcome, that means just 1 foot difference, maybe 1 foot. But if you have a stairs having 4 feet difference, in that case it will be very difficult to climb up in a top building or top of the floor. So here you can see, if the gap is very large, in that case the electron cannot jump from here to here easily. However, if you have difference just only 1 feet, you can climb from bottom to the top of the floor. So as the band gap is quite small, therefore the electron from here it can transfer easily to the conduction band. So this is the simple band energy diagram, but I didn't wanted to show or discuss here. Still I am going to already have mentioned, so in the later I will show another diagram. However, the basic idea, as I have mentioned, that the semiconductor have the band gap. To make you understand the band gap, I have mentioned here all the band gap for. So in case of semiconductor, most of the case the band gap is around 1 electron volt or less than 1 electron volt. That means the difference between here to here, that means this line to this line, you can consider is around 1 electron volt. This is our energy. This y-axis gives the energy. Therefore this gap is around 1 electron volt or little bit less or more. On an average it can have 1.2 or it can have around 0.8 or 0.7 electron volt also. So on an average the band gap between these two, or conduction band and valence band, is around 1 electron volt. So if you apply certain condition or potential difference, in that case the electron can transfer from this band to this band. So But in case of insulator, the gap is very large. It can be 2 volt, 3 volt, 4 volt. So it cannot transfer electron easily. So at T equals 0, they behave like an insulator. That means at very low temperature or 0 degree Kelvin, the kinetic energy of the electron in the valence band is very low. Therefore, they cannot jump electron from the valence band to the conduction band. So they behave like as insulator. While at higher temperature, a small density of electrons excited at finite temperature. So if you apply certain temperature, in that case the electrons can have some kinetic energy. Therefore they can transfer from valence band to the conduction band. Typical semiconductors are silicon and germanium or group 3 to 5 compounds. Normally we consider the or what are most useful semiconductors, that are silicon and germanium. Till now I didn't teach you about the germanium. In last 2 classes I have taught you about boron and silicon, and today we are going to learn about semiconductor, and if I have maybe in the next class I will try to teach you about the germanium. So typical semiconductors are silicon and germanium or group 3 to 5 compounds. So group 3 to 5, that means group 3, 4, 5, these types of compounds are considered as semiconductors most of the case. 2 atoms in primitive basis have 4 electrons is, that means if you have a compound or molecule having group 3 or group 4 or group 5, so if you have a compound of group 3 and 4, a group 3 and 5, in that case they can have overall 8 electrons, that means on an average 4 electrons for each atom. Therefore 2 atoms in primitive basis have 4 electrons, 3 plus 5, so 8, on an average you have 4 electrons. Or even in case of group 4 element or group 14 elements, they have already 4 electrons, so they can have share their electrons to other 4 electrons to make the bond. So on an average the semiconductor has 4 electrons, but if you do some doping, in that case it can have 1 electron less or 1 electron more. So what types of semiconductors we can have? List of semiconductor materials. Some pure elements, what already we have mentioned, that group 14 elements, that means carbon, silicon, germanium, these elements have the outermost electron 4 electrons. Certain pure element in group 14 of the periodic table, so these are considered as semiconductors. And the most commercially important elements are silicon and germanium. Already taught about the silicon, so next class we will learn about the germanium. So the most commercially important elements are silicon and germanium. That means already I have mentioned several times that using these types of silicon and germanium we can prepare different types of semiconducting devices like as different IC, circuit, many other things which are very important for you. That means the people who works with the electronics, especially computer or different types of electronic devices. So silicon and germanium are used here effectively because they have 4 valence electrons in their outermost shell, which gives them the ability to gain or lose electrons equally at the same time. So already mentioned that silicon and germanium has 4 electrons in the outermost shell because they are in the group 14 or group 4a. So when they have 4 electrons, to fulfill their octet, either they need to lose 4 electrons or they need to gain 4 electrons. So they can share 4 electrons at the same time, but many of the elements in the periodic table cannot share 4 electrons at the same time, but silicon and germanium they can. So they if you consider different types of elements, sometimes you can bring one element having one atom, one electron, or sometimes you can bring two elements having two different electrons. So in that way you can fulfill the octet. So silicon and germanium are used effectively because they have 4 valence electrons in their outermost shell, which gives them the ability to gain or lose electrons equally at the same time. Binary compounds, that means already mentioned in the previous slide. That means what are the binary compounds? Binary compounds, you can have binary compounds of group 3 and group 5 elements, or group 4 elements, or some other. Even you sometime you can have group 4 elements or group 14 elements with group 2 elements. That means they have 2 electrons in the outermost, or group 16 elements in the, so they have 6 electrons in the outermost shell. So in that way you can have the possibility to share 4 electrons. So group 13, 15 such as gallium arsenide, group 12 and 16, group 14, 16, and between different group of 14 elements silicon carbide. So different types of binary compounds, that means 2 elements. If you combine 2 different elements to make a compound or molecule, in that case you can consider that compound as a binary compound. Okay, certain ternary compounds, oxides and alloys, that means sometime you may have ternary compound. That means if any molecule or a compound have 3 elements, then we will consider that as ternary. So elemental has only 1, binary compounds has 2, and ternary has 3 elements or 3 atoms in a compound or molecule. Therefore sometimes you can have the semiconductor materials either binary compound or elemental, that means pure silicon or pure germanium, this is elemental, and binary compounds that can be, here we have given some examples, that are gallium arsenide or silicon carbide. These types of compounds can be semiconductor, or sometimes ternary compounds, some oxides or alloys, they can be considered as semiconductors. Okay, this is the simple band energy diagram. Already I have mentioned in the first slide. So here you can see, just this is the valence band, and if I ask for you writing the valence band, energy band diagram in the exam, then you have to draw like this way. What is this? This is our valence band, and this is our conduction band, and this is vacuum, that means outside our consideration. So if you consider this is the valence band, this red, this is valence band and this is the conduction band. So this is the conduction band, this is the gap. Now if the band gap is very large, in that case you will consider this is an insulator, and if the band gap is small or completely overlapped, then you will consider this is metal. And if the band gap is moderate, that means neither very large nor very small, so there is a certain gap but not very big, in that case you will consider that material is semiconductor. And most of the case, as I have mentioned, that the valence band and conduction band, the energy difference between the valence band and the conduction band, this is our this is energy, this scale is energy. So this is the black line, you can consider this is the conduction band. The energy of the conduction band is represented by EC. So this is the conduction band energy, and the top line of the valence band, this is considered as the valence band. So the difference between these two black lines, this is the energy of the conduction band and this is the energy of the valence band. That means the upper level of the valence band is considered as the energy of the valence band, and the bottom of the conduction band is known as the energy of the conduction band. So the difference between the conduction band and the valence band, that means the energy difference between the conduction band and valence band, are known as the band gap. So if you need to have electron transfer or flow electron, in that case what you need? If you need to transfer electron, in that case you must need to transfer electron from here to here or here to the vacuum. So if the band gap is very large, then it is very difficult to transfer electron from valence band to conduction band, or from the here is empty. So most of the case, in case of insulator, the conduction band is empty, therefore there is no way that it can transfer electron to the vacuum or very far away. Why we consider this is vacuum? Vacuum is, that means if you consider a molecule, you have the valence band and the conduction band, but to transfer electron you need to transfer the electron very far away. So we consider that is considered as vacuum. So these are the electronic properties what we have mentioned, and the valence band, energy band diagram. Electronic properties of a semiconductor are dominated by the highest partially empty band and the lowest partially filled band. Actually this is the valence band and this is the conduction band. So if you can understand the electronic configuration of the valence band and conduction band, in that case you can easily describe the properties of a molecule or a material. That means the electronic properties of that material depend on the valence band and the conduction band electronic configuration, or the arrangement of electrons, how many electrons are there, or if the band gap is large or not. So electronic properties of a semiconductor are dominated, that means it is controlled by the highest partially empty band and the lowest partially filled band. So by this consideration we can easily estimate what would be the properties of a material. So what I have shown in the diagram, that is described here, just I will read out. The diagram identifies the almost empty conduction band. Already I have shown almost empty conduction band, just little bit electrons. So this red line you can consider, or red portion, I should not consider red line. This is the red portion. This is red portion, lot of electrons, and here little bit. This is our conduction band, but we have very little bit electrons, so we can consider the partially filled conduction band. So the diagram identifies the almost empty conduction band by a horizontal line. The line indicates the bottom edge of the conduction band is labeled as EC. This is the bottom line, that means the minimum energy of the conduction band is represented by EC. The top of the valence band is indicated by a horizontal line labeled EV. This is our valence band, or the maximum energy of the valence band is considered or represented by EV, valence band energy. The energy of the valence band you can consider like this way, energy of the valence band, and this is the energy gap, this is energy of the conduction band. Okay, the energy band gap is located between the two lines. So in between this line and this line, this is our band gap, which is represented by EZ. Okay, now what are the properties, or just I will show you in general the variable conductivity of a semiconductor. Normally at room temperature, a pure semiconductor is a poor conductor. Poor do not mean that is very they do not have money or something like this. Sometimes we use poor, that means they do not have the certain property. So simply semiconductors are poor conductors. They have their valence band filled, preventing the entire flow of new electrons. So one thing already I have mentioned, that if any element, even for some metal, if the valence band is completely filled and the conduction band is completely empty, then they cannot have free electrons, so then they cannot transfer electrons or electricity. So for some metal also they cannot transfer electricity very well, though they have completely filled valence band. However, without having the free electron, they cannot transfer electron or electricity very well. Therefore, in some case, some semiconductor, they have completely filled valence band, therefore they cannot flow electrons at all. So in that case we have used the term poor conductors. So pure semiconductor cannot transfer electrons or electricity. Several developed techniques allow semiconducting materials to behave like conducting materials. That means some of our recent technologies or idea that scientists have developed, that they can add some impurities. That means if we add some impurities inside the pure semiconductor, based on what our interest, that can be different types of materials, group 3 elements, group 4 5 elements. So based on our interest, what types of conductivity we want, based on that the scientist has designed or proposed several methods and implemented, not only proposed, they have implemented several methods to increase the conductivity of semiconductor. So several developed techniques allow semiconducting materials to behave like conducting materials. That means some of the materials can be used like as conducting materials, though their major portions are semiconducting materials. However, if you add some non-conducting materials in a certain way, that can give you a very high conductivity like as metals. So these modifications have two outcomes. That means if you add some external material inside your semiconductor, pure semiconductor, based on what types of material you are inserting, we can separate the semiconductor N type and P type, two different types. Later I will discuss you the what is N type and what is P type and how we can create the N type and P type semiconducting materials. This refers to the excess or shortage of electrons. That means if you add some dopant, that means some unexpected or external material inside your semiconductor material, in that case you can have one extra electron or you can have a shortage of one electron. That will give you the availability to transfer electron through the substance or through the crystal. An unbalanced number of electrons would cause a current to flow through the material. So if you have some free electron or if you have some shortage of electron, then you can easily collect or take one electron from other. Therefore in that way the semiconductor can transfer electricity through it if it is doped with certain element, either N type or P type material. Okay, now what is intrinsic and extrinsic semiconductor? That means 100% pure or just there is no outside material. If you consider the silicon or germanium, anything, just if there is nothing else except the pure semiconductor, that is known as intrinsic semiconductor. That means a pure semiconductor or undoped semiconductor is known as, or undoped semiconductor or I type. I type, that means intrinsic. I type semiconductor is a pure semiconductor without any significant dopant species present. So if you do not have any material except the pure semiconductor, that is known as intrinsic semiconductor. Actually the intrinsic semiconductor is not good at all for conducting electricity. So intrinsic semiconductor has very less amount of use, so that is not very important. But if you can add certain elements in a controlled way, that will be very helpful. And extrinsic semiconductor is one that has been doped, already added some material during manufacture of the semiconductor crystal. A trace element or chemical called a doping agent has been incorporated chemically into the crystal. So in different way you can add some other elements inside your pure semiconductor. So any material or any other thing which is doped or added to the semiconductor, that is known as extrinsic semiconductor. So the extrinsic semiconductor can have very high conductivity. Sometimes it is comparable to the metal. So some metal have very low conductivity. However, if you have a very good semiconducting material with proper dopant and controlled ratio, that means what exactly you need, in that case the semiconductor or the extrinsic semiconductor can be compared to a metal because their conductivity increases quite large. Sometimes if you add a trace amount of semiconducting material, in that case the conductivity increases from 1000 to million times or even more. I do not I had some slide, but I am not going to show you that if you add certain amount of dopant, how much the electricity increases by counting the number of electrons. But as it is not very important to you, so I am not going to show you. Just I have mentioned that if you add some dopant into a semiconductor, then the conductivity increases around 1000 times to million times, that means 10 to the power 6 times or even more. So the conductivity increases very high, and you must need to control the amount of semiconducting materials what you are adding. So to prepare a semiconducting device, you may need certain conductivity. So if any semiconducting device you need a certain conductivity, but if you add more elements, more dopant inside your semiconductor, in that case it can transfer electrons more than your expectation. So in that case that can be dangerous. So you need to know exactly how much dopant or how much external material need to be added inside your pure semiconductor to get your expected property. So if you add any element, that cannot give you your desired condition. So you need to think about what I want to make and how much electricity need to be transferred through the semiconducting material. Based on that you have to choose a material, external material, and then you have to add a specific amount. How much? 0.1 gram or 0.01 gram or 0.002 mole or whatever. Just you need to calculate exactly what is the electricity will be after addition of the extrinsic material. So you need to add just that amount, neither less nor more. So if you do not have the proper number how much external material need to be added, in that case that can be dangerous. So before using in any device you must need to measure what is the conductivity of that material, so it can handle your instrument or not. Okay. In an extrinsic semiconductor, mainly the dopant provide the charge carriers. Actually for a semiconductor, pure semiconductor, there is no charge carrier. But when you have added some dopant, either it can have one extra electron or it can have one shortage of electron. So if you have one shortage of electron, then we will consider this as a hole, and if you have free electron, then excess electron. So this excess electron can be, or the hole, that will be considered as the charge carrier. That means who will transfer the electron, that is considered as charge carrier. So based on what is the property of the semiconducting material, we consider two different types of doping agents: an electron donor dopant and electron acceptor dopant. Electron donor, that means it has more electrons, it can donate one electron to other one. That means it may have 5 electrons, so it can have one electron extra. So electron donor dopant and an electron acceptor dopant. So that can be a group 3 element, so it will have 3 electrons, and that means if you replace one semiconducting material from the some pure semiconductor by a group 3 element, in that case you can have an element or atom which has 3 electrons, or that means 1 electron less compared to the semiconductor. So that will be our electron acceptor dopant. It can accept one electron from other element. So an extrinsic semiconductor which has been doped with electron donor atoms is called N-type semiconductor. N-type, that means you have more electrons. It can donate an electron, so that is considered as N-type semiconductor. And another type, that means who has the deficiency or shortage of electron, that is considered as P-type semiconductor. Okay, for a N-type semiconductor, majority of charge carrier is the crystal. In the crystal are negative electrons. So I have already mentioned that for a N-type semiconductor you have more electrons than the normal. So in a pure semiconductor you have 4 electrons for each element or for each atom. So if you replace one element or one atom, in that case you will have 5 electrons in that atom, so 1 electron extra. So that 1 electron can transfer to the all over the crystal, therefore that behaves like an free electron, therefore that can be considered to help to transfer electricity. For a p-type semiconductor, majority of charge carrier is in the crystal are positive holes. That means we have mentioned that for a p-type semiconductor we will add some dopant having 3 electrons in the outermost shell, so they can have the electrons 3 electrons or shortage of 1 electron, therefore that we will consider as hole, the place where 1 electron can be set. That means for a p-type semiconductor, majority of charge carrier in the crystal are positive holes. Now